Good afternoon, DEF CON. How's it going? I'm tired, that's all right. So this is generating ROP payloads from numbers. So please join me in welcoming Alexandre Moneger.
Hello everyone, thanks a lot for attending. So basically today I'll be talking about return-oriented programming and how to generate payloads using numbers. So a little bit about me first. I work for Cisco Systems in the UK. I'm a security engineer in the Cloud Web Security Business Unit, which is basically just a big cloud proxy, which has got nothing to do with what I'm going to talk about today. Personally, I'm mostly interested about bits and bytes and low-level stuff, and the usual disclaimer: the research was done on my own time, and they do not reflect the opinions of my employer, or they're just myself. You can't hear me? Okay, sorry. All right, is it better? Okay, so basically I'll go through a brief ROP overview. So what is it? Why do we use it? And why has it kind of become essential today? The automation basically of the ROP payload generation, why do we want to do that or not, and what are the challenges with it. Then I'll go into a little bit of so the core of the subject, which I've called number stitching, which is basically a possibly new way to generate ROP payloads from numbers instead of from strings. So I'll go through the goal, what was I trying to achieve, why I did it. How I found the gadgets, and basically the core of the problem, which is the coin change problem, which I'll get back to later. And then I'll have a quick chat about the pros, the cons, the tooling that I'm releasing, and any future work. Okay, so I'll have a very brief introduction about ROP, just so that I'm sure that everybody understands what it is. So basically, before in the old days, you could just attack, exploit a vulnerability using, just a bunch of shellcode, and you could just execute it anywhere. Unfortunately or fortunately, nowadays you can't do this anymore, right? You can't execute shellcode in memory just like that. So historically, we got to a point where we got to return-oriented programming, which is basically, instead of executing stuff through a shellcode, use the target binary to execute code for you. So this means that you're not executing code yourself, you're asking your target basically to do it for you. All right? So basically, I'll just come a bit back on basically what I wanted to achieve also. So basically, what I wanted to achieve was to only use gadgets from the compiler or libc stubs. So as I was saying, basically, when you look for gadgets and instructions, you're going to get your program to use them. And so what I wanted to do is take it a level further and abstract it a bit more, and basically be able to use instructions generated by the compiler or by libc to exploit the vulnerability. And so I'll try and generate the payloads basically as usual, putting them in memory and using them. So coming back to my ROP overview, so we know that we want to basically reuse instructions from the target binary in order to bypass ASLR and XOR W. So why we use ROP basically is just that we don't have a choice basically. The memory protections have got much better, we can't do without it, and so we use it. The level of complexity is much higher, so if we could avoid it, it would be nice, but we can't basically. It maintains control flow using the stack pointer and not the instruction pointer. I won't go into the details, but basically this is how you maintain control over the flow of the program. And ROP is multi-staged more or less by design. It's that you've going to have a first stage, which is going to be using the instructions from your target binary to generate a payload for you, right? So that payload, you're going to put it on a custom stack you're going to create within the program. So your idea is, okay, let's take a tiny piece of the program and put some instructions there which I'm going to execute later. So that's your your stage 0, the first phase basically, which is grab some stuff, put it in a zone in memory, and when you're finished doing that, change the control flow and execute that later. And as I said, it's more or less the only way around today's OS protections. You know, if you look at all the IE exploits and all that stuff which happened in 2013, they all use ROP to evade all those memory protections. So just a bit of vocabulary. What is called a gadget basically is just a useful instruction inside the target binary. So it's going to be a very small piece of assembly with a return instruction at the end. So that is what you're going to call to execute code. How do you find them basically is that you go over your binary, you look for every return instruction, which is 0xC3, and you disassemble backwards from that, and that will give you basically what you can work with. So to do that, there are many good tools available, ROP Gadget, ROP Me, which basically just go over binary, will give you what gadgets you can use to attack it. And obviously the number of gadgets you can find in a binary is completely dependent on the size of the binary. So if it's huge, you've got a big chance of finding a lot of gadgets you can use. If it's really small, obviously you've got much less and it becomes much harder. So once you've done your stage 0, you've built your fake frame, your fake stack frame basically in memory. You want to transfer control to that payload because that's what you want to execute, right? You want to get a shell or get whatever you want. So shifting control from the current control flow into your stack frame is called stack pivoting, basically, and it's a way of redirecting control flow so that you basically get then your code to run once you've built it. Okay, so I'm going to talk about automating the payload generation, which is basically how from a program can I take bits of memory and create that fake stack, which I will later execute. So this is the classical approach of what happens is that you find, a bunch of bytes in memory. So the bytes you're looking for are obviously your shellcode bytes, right? So you've got a shellcode you're going to start from or something you want to achieve, a bunch of function calls you want to call, and you're going to look for those bytes in memory and copy them over to a stack you control. Once you've done that, you get execution on that stack. So to achieve that, you're going to look for some particular gadgets, which is a move gadget. So you're going to try and move something from a register you control to a zone in memory you control. Or you can use a bunch of functions if they are exported by the target binary, which is not always the case. So you've got a bunch of potential problems in this. It's that you're counting basically on the availability of a move gadget. In real world, you've generally got it. So in big programs, it's not a problem. It can require some GOT dereferencing, which I won't speak too much about, but that's if you want to get basically call a particular function. And also you're expecting some bytes to be available in memory. So typically in shellcode, you're going to look for 0x80 for your interrupt number. And so you're expecting that number to be in memory because otherwise you're not going to be able to build your shellcode. If that number is not there, it generally requires some manual work to get the missing bytes. All right, so if we look at a shellcode here, which I took, basically you can see that if I look for the bytes 7368, I can find them in the program, so that's nice. I can find those 2 bytes, which are part of my shellcode, and I'm going to be able to use them. If I look for something different, basically, for example, 682F. I don't find that in the program, right? So that means I'm going to have to do some manual work, manipulating some bytes to get that. So back to the move gadget, basically. Very small binaries do not tend to have many move gadgets. So it means that the automation of the payload is complicated. And in the case of this particular gadget I'm showing, you've got a problem sometimes with null bytes. And basically, it also needs some extra work to get rid of them. Okay, so here I'm going to introduce number stitching, which is basically, I was asking myself the question, is it possible to exploit a hello world type vulnerability with most memory protections enabled, right? I won't consider stack canaries and all that in this talk. But basically, a gross programming mistake, you copy, a user supplied argument with string copy and you get a buffer overflow or something like that, is exploitable with everything enabled. And also I was wondering, can I exploit this independently of what the program does, right? Using only the compiler or libc stubs. So, in other words, is it possible to not rely at all on the target binary to generate a ROP payload? So I'll go through a bit like how a program is built and how it's linked and what happens, and we'll see what we get. So basically all the following of this talk is going to be based on the gadgets I've been able to find here. Basically all the other stuff was done due to the gadgets which were made available to me. So if you just take a hello world, right, and compile it, so what happens, right? If you look at what your program actually contains, you see there's a whole bunch of other functions which you did not intend to be there. So, the start, you've got libc, csu fini, and all that stuff. So where does that come from, and can you use that? So if you look basically at link time at what happens, the linker will call libc.so. So you'd think that it's a dynamic library, but it's actually not. It's a script. And basically that script has got a static library in it. So meaning that when you compile your program against libc, you're going to have most of your functions dynamically linked, but also going to have a subset of those which are statically linked into your binary. So if you look at that, there's quite a few functions in there which you could possibly use, right? So all this basically is, if you use it, it will be statically linked into your program, meaning that those gadgets will be at fixed addresses if PIE is not enabled. So the problem I had is that those functions, they're not always used. They depend on various compilation options and linking options. And anyway, I just looked for gadget through them and I couldn't find anything useful, right? So I think it's good also to say that, what you weren't able to achieve. So basically, looking for gadgets in that completely failed and I wasn't able to achieve anything. So basically I went back to my binary and said, all right, is there anything else which is added, which I could use? And so basically I looked at the binary and there's a bunch of functions which are added by GCC in some cases. So they've got no symbols attached to them, so it's kind of hard to figure out what they do, but they're just a bunch of anonymous functions which are inserted into your program. So if you look at the disassembly of your program, you'll see that there's some functions where there's no symbols associated and they're just there basically. Those functions seem to relate to profiling, and so that's why they're there basically. So what was surprising to me is that profiling seems to be enabled by default on some distributions, and so that this stuff is actually statically linked into your program and all these little tiny pieces of assembly are put into your program without you knowing about it. So to check what the default options are for GCC, you can have a look at, GCC-Q-V will dump basically the list of compiler options that are done by default by GCC, and you might find some stuff interesting. So basically, this work was done for GCC 4.4.5, which is pretty old. And basically, I looked for gadgets inside the code that was embedded by GCC into the target binary. So based on that, I kind of disassembled those functions, and I end up with this stuff to work with. So this basically is only generated by the compiler. It's not code which is generated by the target application. So you can see that I've got a bunch of stuff that I get to work with. So the first one allows me to control EBX, so put a random value into there and control that. The other one, leave, allows me to pivot the stack when I've achieved control and that I want to execute my shellcode in the end. And then the two others, which are kind of the meat of the talk, is that there is a write to memory. So basically if through control of EBX I can write the value which is in EAX to EBX. So meaning that the value in the register I can dump it somewhere in memory. And I've also got the other way around, a write to registry, meaning that a value, by controlling EBX, I can grab a value from memory and load that in EAX. Okay, so that means that in short, as an attacker you control EBX and that's about it, right? So you have to find a way to achieve control of EAX also. Okay, so this, so basically the further part of the talk will just focus on those two instructions, on those two gadgets, and basically how I use them in order to achieve code execution. So basically we've got a useful gadget here which is add memory to a register. I removed the trailing stuff and all that because it's not necessarily interesting. So you control EBX, so it means that you can grab a value in memory and load it into a register. Okay, is that useful? Well, you don't control what's in memory necessarily, so it's at first I didn't think it could be potentially useful, but actually it is. I'll come back to this later. So now the reverse, basically, once I've got a value I'm interested in a register, I can dump it into memory, right? So this allows me to create my fake stack frame. So assuming that I control EAX, I can build a fake stack frame at the addresses pointed to by EBX. So that means that by chaining these calls, I can copy my shellcode into a frame I control and then trigger execution of it. So basically, as this is the more general approach to ROP, is that you're going to choose a spot in memory where you can build your stack. So, the memory properties you want is that obviously you can write to it, and so with today's memory protection, you can either execute or you can write. So you're going to choose a zone where you can write. If you look at the previous instruction, it was an add instruction. So I have to find what is called a kind of a code cave, which is a zone where which is just padded with null bytes, so just a bunch of zeros. So that way when I add it, I just add to 0 and I still get the same value I want. So it avoids like further computation. And then you choose the shellcode you want. So just pick a shellcode, anyone you want, a setreg ID for binsh or reverse shellcode or whatever you want, and basically just just hope that you're going to copy that shellcode to a frame you control and then execute it. So now the unusual approach I'd say to do this is that I chose to since I had to deal with arithmetic operations such as add, I chose to actually see the shellcode not as a string but as a number. And so basically if I cut it into small pieces of 4 bytes on 32 bits and 8 bytes on 64, I just cut the shellcode into 4-byte chunks and then basically I interpret each chunk as an integer. So that just says basically take a string and it's actually a number. And so if you keep track of each of the index basically of each chunk, basically which index your number is. And what you want to do is, since you're going to always be adding, you want them to be ordered because you always want to go from smaller to bigger. So basically you just order them. So you take your shellcode, cut it into little bits as numbers, and then basically you keep track of their position and you reorder them from smallest to biggest, right? And then once you've done that, you compute the difference between each chunks. So that will give you basically deltas between your pieces of shellcode, and it will keep your shellcode basically monotonically increasing, just meaning that each time you add a value to your register, it's going to always go up. So what this looks like, if I take this example, so at the top you've got a shellcode, right? Just a string of hex. So if you take that as a number and reorder it, you get to line 2 basically. So if you see the end of the shellcode has been shifted back to the front and I've ordered all that together. Alright, so they're ordered in increasing number. If you take the difference between each, basically you get small deltas. So you see basically at the last line that position 3 of your initial shellcode is now at position 1. Position 2 is actually is actually 2 minus 3, and it's put at position 2, and etc., right? So your shellcode is now represented as increasing deltas. So if you take your initial value and add the delta, you find back the value of your shellcode. You do that again, you find again the next value of your shellcode, do that again, find the next value, etc. And once you've reached that value, you want to dump it to your fake stack, but you want to dump it in a way that you remember at which position it was initially, right? Otherwise, you're going to write it at the wrong spot. So once you do that, you just repeat, you repeat, and then eventually you've copied what you want into a zone of memory. So as an example, say you want to copy the number 0, 1, 0, 2, 3, 4 into memory. So you find that number in memory. So for the timing, I'm just assuming that it's there, right? I'll speak later on what happens if it's not. So basically you assume that a number's there in memory, and you load the address of that, and basically you copy that into EAX. So you've achieved loading a value into a register from memory, right? So that's kind of easy. Now you've got the value you want of your shellcode, so you want to dump it onto your fake stack frame. So now if you look at that guy was actually at position number 3, so you actually drop it on the stack at the right position. And now you're going to look for the next number, which is, you know, the delta, which is in this case 040404, and so you assume that that also is in memory. You take it, you sum it, and you get back to the same value, and you dump it. And you do that over and over again, and in the end, basically, you've achieved building a shellcode from a bunch of numbers that you found out in memory. So now it comes to the problem of how easy is it to find shellcode numbers in memories, because basically if you take your shellcode and look at it as a bunch of numbers, it's actually pretty high numbers, right? It's going to be, if you look at the example I've put there, 6A, 31, 58, 99, if you take the string, I mean, without talking about what happens behind, but you just take the string and, you know, integer and 2's complement and stuff, it actually ends up at 66, A7C, 96, which is actually a pretty high number or negative number. But we're relying here on the fact that that will be in memory and that we can copy it, right? What happens if it's not? So here, basically, the next part is just, all right, I've got that value. Well, I'm hoping for that value to be in memory, but it's not. What can I do, and how can I build it? So basically, the answer is that it's not very easy to find big numbers in memory. They're not. So I had to look at a bunch of programs, and I saw that they're basically not really there. So here I put a small example of looking for, you know, 01, 02, 03, 04 in GDB, and that it just doesn't yield anything. If you look at multiple programs and search for those numbers, they're not really there. So I had to find basically a different approach. So the approach was, my idea was that if I can basically scan memory for numbers, and if I can find a way to add them together to end up to that chunk value, then I'm fine, right? So by definition, memory, you know, has got a crazy number of numbers in there, right? If you look at individual numbers, it's got heaps of it in there. So the approach is basically take a file, take, you know, its read-only segment, and basically just scan it for numbers, right? So just, you know, look at the beginning of it, see it as a number, shift it by 1 byte, see it as a number, shift it as 1 byte, and see it as another number. So you scan all that segment, just looking for a bunch of numbers, right? So where I decided to look up for was basically in the read-only segment, because obviously you don't want those numbers to change at runtime. Here they come.
Keep going.
All right. So basically, yeah, I looked inside the segments which were read-only, so that basically I knew that at runtime those numbers would not change at all, and excluded all the read-write segments, basically which were going to change. So basically, if you don't have position-independent code, the addresses are constant. Thank you very much.
Show some love for our first-time speaker at DEF CON.
Thank you very much.
Welcome. Thank you very much.
Thank you too.
What do you guys think of his graphics? I'm sorry, that was low.
That's all right. So yeah, basically, yeah, the read-only segment, basically, to find your numbers. So what you do is scan that read-only segment, look for the numbers, shifting by 1 byte each time, and you keep track of their addresses, right? And so what you end up is with a whole bunch of numbers, and the problem seems pretty simple, is that how do I add up, these random bunch of numbers to find the chunk I want, right? So all you're looking for is finding the best combination of numbers which add up to a chunk. So this problem seems pretty simple because, for a human, like, we do it all the time. But actually for a computer, it's pretty crap to get it to do that. And it's basically called the coin change problem. So it took me a while to figure out that it actually was what I was looking for. So the example is really simple, right? You buy just an item at, 425 euros and you give a €5 note. I'm from Europe, right? And, what's the most efficient way to return change on that? That's something we know how to do pretty easy. In Europe, we'd give back a 50-cent coin, a 20-cent coin, and a 5-cent coin, right? So basically that's the coin change problem, is that what's the most efficient way of giving money back basically to someone who's paid you an item. And so basically if you look at this problem in dollars, the answer is different, right? You're looking for same thing, 75 cents. So basically in the US you'd give a $0.50 and a quarter. So you see that here the solution basically depends on your coin set, and so it depends on the numbers you found in memory. So solving the problem for a human or for a cashier is something pretty simple. Solving the problem for a computer is a bit more difficult. So basically you can achieve an ideal solution to the problem by using dynamic programming, which basically will give you the most efficient solution. So, maybe some of you guys have done that at high school. It's a pretty simple problem to solve when you've got small numbers. The problem is, since I'm dealing with pretty big numbers, is that dynamic programming doesn't scale and it just kind of blows my memory. So I can't get to scale it for massive numbers yet. So I had to use a different approach. So I used an approach called the greedy approach, which is just slightly different, which basically achieves the same thing, but won't give you the optimal solution, right? It will give you a solution. And so how it works is that it's just really simple. It's just like you take the biggest coin which fits in the interval and then just add and add and add. And so one thing that we're kind of lucky with is that in numbers you've got you've got many small numbers, right? Number 1, 2, 3, 4, 5, all that is, it's like you've got heaps of them in there. So basically you always can achieve the greedy approach, which is kind of nice, but it's suboptimal. So coming back, to the 75-cent problem, looking, with, trying to return 75 cents using the greedy approach, basically you just go down the list of your coins and take the biggest one which fits in this case, 50 cents, 20 cents, and 5 cents. So basically all my tool does is that you give it a number in memory, it will scan all memory, and it will try and find you the best solution for this. So basically I wrote a tool called ROP, which basically is just trying to find you a solution to the coin change problem. So basically you give it a number, you give it and it will basically throw you out all the addresses where those numbers added together end up with a chunk, right? So if you look at this back into the context of what I was talking before, here you're basically looking to add up a bunch of numbers in memory to reach a chunk of your shellcode, right? So this is what ROP will do. It will give you basically that. It's got a bunch of extra features, can ignore null bytes, exclude numbers which you don't want in the coin change solver. it can print all memory address pointing to a number, pointing to 0, etc. I mean, all these features are basically not critical. They just make your exploit dev easier because you can exclude null byte addresses, you can exclude addresses which are not in your range, and etc. So an example usage is basically find me the address of numbers in the segment containing the text section, so a read-only section, which added together solve the coin change problem. So here, if you look, it will spit out at the lower part, it spits out 5 numbers basically, and if you add those together, you get your target number, which is your shellcode chunk. So if we look back at this, basically, it will give you, the individual parts of the number which sum together get to your shellcode. Right, so here I just showed that if I re-add all the values together, I get my initial value. So now coming back to my gadget, it's that here, by putting the value I want in EBX, and by adding repetitively, I can add the value, I can get to the value of my chunk. Okay, so if I put all this together, so basically, so you take your shellcode, you cut it, you order it, and you take the deltas. You look for numbers in memory, and basically you add them together until you reach the value of a chunk. Right? So here it means you've reached the value of your shellcode. So once that chunk is reached, you basically just dump it onto a stack frame you control. And you repeat that until the shellcode is complete, and in the end, you just transfer control over to your shellcode. So I wrote a tool also which automates all this process, basically where you just give it a shellcode and it will spit out some Python code to generate your payload exploit. So what it does is basically you give it an input shellcode, so anything you want, you give it a frame address, so where you want to copy your data to, right, which will generally be the data section. It takes care of all the boring details, right, which make your life hell, so Indianness, 2's complement, padding, blah, blah, blah. And it will spit out a bunch of Python code which generates your payload. So if you're familiar, with all the CTF tools, ROP, gadget, all that stuff, it does something pretty similar to that. Now what it does also is that, for the timing we've copied our payload to a fake stack we've got, but that stack is read-write for the timing, right? So what the tool will do is that it will add a small mprotect read-write stub frame before your payload. So what it does is that basically it will allow to change the memory permissions at runtime so that your shellcode can run. And so it's got a bunch of additional functions, like it can start with an arbitrary EX value, and it can look up numbers in sections or segments depending on what you want to do and all that kind of stuff. So a bit more on why you need an mprotect stub, basically. So you've copied your shellcode into a zone of memory which is read-write, right? So if you return execution to that, it's not going to be able to execute, right? You're just going to get a fault from your processor because the memory permissions are wrong. So you need to make that page kind of read execute or read write execute at runtime. So this is where mprotect kicks in. It's just a standard Linux libc function, which allows you to change memory permissions at runtime. So basically I just add a small mprotect stub in the front of that, and once that has executed, it will jump back into your shellcode. So an example usage is basically, to copy a binsh shellcode to a fake frame located in the data section, putting an mprotect frame and looking up segments in the read-only segment in a binary, you end up basically with this command. And so all this basically will spit you out a bunch of Python code which will just once run will basically generate your shellcode. So I didn't put the output on the slides because it's pretty verbose and it's just a bunch of code which isn't very interesting. I put it on the CD though, and I've got an example on GitHub if you want to have a look at it. So if we have a look at GDB, at what's happening inside GDB basically, you'll see that I put the values in yellow. They're the values which are basically being copied. So if you look at those values, the first one basically 0x7 is a read write execute for the mprotect frame. And so basically that one is written at its proper index. The next one is 0x80, right, which is the interrupt number, and you'll see that that guy is written completely at the end of the stuff. So this kind of shows, the tracking of the index and where stuff has to go to rebuild your shellcode. And so then I write 0x1000, which is the next, biggest number on the shellcode, and it will write it back, at a different index, etc., etc. So if you continue that, you continue that execution 10 times, just to see it go a bit faster, you'll see that there's a bunch of missing zones in orange, basically, which will be filled in later. So this is just kind of to show that the shellcode is built kind of out of order. And so the end shellcode is basically, your shellcode is complete in memory with a read, write, execute mprotect stub just before it. So there's a bunch of pros and cons to this technique. I don't know, I was wondering about this and etc. If it's got a real use case scenario. It's just something I wandered around with and I found it nice, but I don't know if it's actually useful in real life. It's got a bunch of pros though. It's that it can encode any shellcode. You don't have a null byte problem because basically all you're dealing with is addresses, right? You never actually look for values. And you never pop values into registers, just addresses. The lower 2 bytes of your address are controlled, basically, and so you can exclude those values if you don't want them in your addresses. And obviously, the initial goal was that you're not affected by RelRo, ASLR, or XOR W. So basically, it will allow you, to bypass all those memory protections. The cons basically is that the payloads are fairly large, right? Because you're generating you're adding, multiple values, right, to reach a value of a chunk. So up to, 5 values together. So that requires quite a bit of iterations to get there. So what that means is that those iterations, they transform into, a code length, basically. So your payload grows. So your stage 0 can get pretty big. So that's a pretty, pretty big con. So the further usage to this is that, let's imagine that, here we were looking at EAX. Here I'm still looking at, the specific case of GCC 4.4.5 is that I achieved control of EAX through, through this technique. But basically, one thing I had is that sometimes EAX, the initial value you've got in there changes depending on, on your user input data. So one nice trick is that if you control EAX is that you can more or less get a value you want into there through during just a random function call in the PLT. And since, in the Linux std call ABI, EAX holds the return value of a function call. So basically, if you do any random function call and make it fail or succeed or whatever, you can kind of control the initial value you've got in there. So now I tried to take an approach to shrink the size, basically, of the stage 0. So one approach was basically that instead of loading the whole shellcode in memory, what I could do is just create some kind of gadget table, right, at the location I wanted. So instead of taking the whole thing, the whole shellcode, which is, a big number of bytes, and just ditching it there, what I can do is, instead of that, load a bunch of additional gadgets and use that as a table to further continue my exploit. So for example, say that, you've got your exploit and you'd like to have those gadgets I put in there, right? It's the opcodes I put on the right. So basically your shellcode becomes, 59C3, 5B, blah, 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 blah. So if you load that, you use number stitching, and ROP stitch to generate that and put that in memory, then you can actually call them directly from, from a stage 0 payload or from your payload. And so that way you can kind of insert additional gadgets within the target's memory space. Which is kind of practical. And so, yeah, since, the tool can change your memory permissions, it will work. And then you just call the gadgets from your table, or it doesn't have to be necessarily gadgets, it can just be bytes, right? You can just add a bunch of bytes there and it increases kind of your availability of your bytes. And so, yeah, you have kind of the ability to load any gadget or byte in memory just using a bunch of memory addresses. I haven't automated that part in the tool yet. It's just kind of, on the side. So future work. So basically, I'd like to continue having a bit of a look on numbers, and basically if they're available to memory and not subject to SLR. So check a bunch of binaries with PIE, see if I can figure out if anything comes up. Realistically there shouldn't be, but you never know. Maybe something will come up. And basically search for gadgets in new versions of libc and GCC. So it seems difficult, but I might find a bunch of gadgets in there which could be exploitable, and allow to have that separation basically of exploiting the program through its kind of dependencies in a way. And on the tooling side, basically, I'd like to get a dynamic programming approach to work with large numbers. I don't think it will be completely possible, but I'll have a look into it. To add 64-bit support, I mean, here, regarding the methodology, it's pretty simple, right? The numbers are just bigger, so it doesn't change anything. The problem will be with the mprotect stack frame, which might be harder to introduce. And I think basically that there'd be an advantage in introducing a kind of mixed approach. So, possibly integrating this in other tools which already do their job really well. So, ROP gadget can generate a payload once it's got everything from a string, but maybe try and automate finding the missing bytes basically using this technique, which means that you'd have a real automatic payload generation. That's obviously if they're interested. And basically I'd like to also introduce, in the tool basically the concept of, gadget tables and, introducing random bytes at random addresses. So just, to summarize, what I wanted to do was basically, to achieve exploitation without using gadgets from the target binary, but from, stuff introduced by the environment. That took me down the track, giving me those two particular gadgets that took me down the track of having to kind of scan memory for numbers and find ways to add them together to achieve what I wanted. So if you want to have a chat about it, or if you've got any ideas, or if you think this is useful or not, just shoot me an email. And if you want to try out the tool, it's available on GitHub, so give it a shot. Thank you very much for your time and for listening through this, and have a good DEF CON. Cheers.